Hi, this video will cover section 10.7, polar coordinates. The objectives for this section will be to plot points in the polar coordinate system and to convert points from the rectangular coordinate system to polar form and vice versa. So we will start easy with just points, and then from there we will move on to equations. So we will convert equations from rectangular form to polar form and vice versa. So just to give you a very quick intro of what we are talking about, when we talk about the rectangular coordinate system, we are referring to the one that you have been working with. For example, in a two-dimensional space, it will be the XY plane. So that will be rectangular coordinate system. Now with polar, we will have a center, which is actually called the pole, and then we will have concentric circles, meaning with the same center. And from there, we are going to be graphing things. And I mean, it's going to be a little different. Oops, that should be exactly at the center. In the rectangular coordinate system, we refer to that as the origin. So right here, it's considered the pole. And we also have each circle here has a different radius. So for example, the first circle has a radius of 1, radius of 2, and 3, and so on. And we will also consider direction when we do things like that. Now, what we use here for our coordinates will be r comma theta, r for the radius and theta for the angle. And that's how we're going to be plotting points. For example, if we had an angle of 120 degrees, for example, it will be something like that, starting from here. And if the radius was a 2, then the point will be right here on the terminal side of that angle in standard form. If this was to be, I think I said 120 degrees, and if the radius was 2. So that's how we will graph something like that. When with rectangular, we have x and y. And if we had a point such as, let's see, it's not going to be exactly correct, but let's say that we have -1 and then 2. Perhaps that point might be located around the same as this one, and it's not accurate, but just to give you an example. So we're going to learn how to go from rectangular coordinates to polar coordinates and vice versa. So from polar to rectangular, and we will be doing that with equations as well, and also we will be looking at their graphs. So as I already demonstrated, you've been working with points like x and y, and we call that the rectangular coordinate system, where x is representing the horizontal distance and y is representing the vertical distance. So just like I was drawing on the previous slide. So in this case, we're going to use the different one, and we refer to it as the polar coordinate system, and we have a series of concentric circles. So important and new vocabulary, and we have the fixed point that it will be referred to as the pole, and that will be at the origin if it was a rectangular coordinate system. So we refer to it as pole, and then construct from O an initial ray. So we start from here, and we start with the polar axis. just like when we graph an angle and standard precision starts on the positive x-axis. So these angles will start on the polar axis, and then they could be positive or negative, but remember, always start on the positive horizontal axis. Then each point P, capital P, that's what we will use, in the plane can be assigned polar coordinates, and we will refer to those as r, comma, theta. So r is the radius of the circle, and that will be the distance from the origin, from here to the point. So that's what the radius will be. And theta is going to represent the directed angle counterclockwise if it's positive. So in this direction. And it starts from the polar axis, so from the horizontal axis, to the segment that is formed from the points O and the point P that is here. So that will be the segment from one point to the other. So the angle, which we call a directed angle, is the angle in between polar axis and the segment that forms the terminal side of that angle. So we're going to start very easy here with example 1, and we're going to plot some points in the coordinate system. So the point that we are going to plot has a radius of 2, and it also has the angle of pi over 3. Remember, pi over 3 is 60 degrees, in case you don't remember. So you could see that it is already being graphed here. So the way it works is you start, of course, on the polar axis right here. That will be the initial side of the angle, and the terminal side will go those many radians, so which is right now pi over 3 radians, or 60 degrees. And so that forms the terminal side of the angle. And what we do is we count from the origin. We have to count 2 units because the radius is a 2. So from there we count 1 and then 2. And so that right there is the point. So the only thing, everything that I drew with blue and pink and highlighted with yellow, that is not the point. The only point is what I highlighted in yellow, just that single point. So like I could go and get rid of everything else, and that will be the only answer. Now, it's important to notice that some points may have, for example, a negative radius. That is possible, or they may have a negative angle. So another way for me to represent this point, the point that we see here, could be by writing, let's say, if I want the point to be here initially, but then I want it to be located where the previous one was, the one highlighted. What I will do is consider an angle that goes, of course, starts from there, and it goes all the way here in the counterclockwise direction. And for me to move that point, this purple point, to the other side where the one in yellow is, what I will have to do is just use a negative radius. So this will be -2. And for the angle, it's going to be pi over 3 past pi. So it's pi plus pi over 3. So that's going to be 4 pi over 3. So that's another example of how, so when you make a radius negative, what happens, it just takes that point and it reflects it across the origin or the pole in a straight line. So that's the difference when you have a negative radius. We could have also used, let's see, we could have used a negative angle. So for example, um, if we have a negative angle, I could say all the way here in the clockwise direction to here. And so that angle will be, let's see, negative 2 pi plus pi over 3. So this is negative 6 pi over 3 plus pi over 3. Just to get the difference between that. And so that will be negative 5 pi over 3. And the radius that we will use if we wanted to land at that point, now I'm going to highlight it in green, then the radius that we will have to use will be also positive 2. So there are many ways that we could do this. We could also use, I'll explain one more, a negative angle. Now I'm marking it with green. And that negative angle could be negative 2 pi over 3. And the radius will have to be negative 2. So there we go. We have 1, 2, 3, 4 different ways to graph the same point. So now let's try to graph this one. And we have the point with a positive radius of 3. And we have the angle of negative pi over 6. So we know that we're going to go in the negative direction. So we always start at the axis, that is the polar axis. And then we move pi over 6 radians in the negative direction. So that's why we go clockwise, the same direction as the clock. And remember that in degrees will be equivalent to negative 30 degrees. So that will be our angle, and because the radius is positive, you could see how we will count from the origin. We will count 3 circles. So 1, 2, and 3. And so that will be the point. So let's think about what other way we could graph this besides we already have 3 comma negative pi over 6. So let's see, we could take, let's try the positive angle first. So we could go in the in the positive direction at r equals 3, which will be the third circle. And that in radians will be equivalent to pi over 6 before you get to 2 pi or 12 pi over 6. So it is 11 pi over 6. And the radius is still positive. Now, if I was to change the radius to something negative, it will be a point located here. But we wanted, actually, if r was 3, it will be there. And if we had an angle that was working, let's say from here to here, and that direction. And so that point will be pi over 6 before you get to pi. So that will be 6 pi over 6 minus pi over 6. So it will be 5 pi over 6. So that could also work because the negative radius will send that point here to where I'm going to highlight with yellow again, right there. Okay, so let's move on to the next one. And now we have positive radius still, and then 11 pi over 6. Oh, and that just coincidentally happens to be the one that we have here in green. So let's just mark it again. So that will be starting here. We go 11 pi over 6 radians positive in that direction. And the radius is 3. So that's why we're on the third circle. Now, I'm going to just clean this up a little bit. I think I have a lot of mess. So I'm going to graph it again. So we started in the polar axis, but because our angle is negative, we go in the clockwise direction. The radius is 3, so we're going to be on the third circle. So we go in this direction, and there we have our point right there. And then, of course, we already have the other representation with positive radius and a positive angle, so it will be the 11 pi over 6. And then we had another one here, which will be 5 pi over 6. I'm going to just draw it here. So we could go 5 pi over 6. So we start here. And then on the third circle, we will go right here, about there. Positive angle. And then our point will be right here. But since the radius is negative, it reflects it across the origin or the pole, and the point will be here. So it kind of like just takes it to the opposite side. So there you have 3 ways to represent the same point. So in rectangular coordinates, each point has a unique representation. And as you can see, that's not the case for polar. We could have different representations, such as the 3 we have here. Or so, for instance, the coordinates r theta and r theta plus 2 pi represent the same point. So remember from the beginning of the summer or the course, we looked at how the period of the radians of one revolution were equal to 2 pi. So if you keep adding 2 pi or 1 revolution, then those two different angle measurements will have several things in common. And one of those will, of course, be the location of them. So saying 2 pi will be the same as 4 pi, or, well, for certain purposes. But it will be, the terminal side will be located at the same place. So they are, I guess you could call them coterminal as well. So if we keep adding 2 pi to our representation, so for example, if I take this one here, let's see which one. Let's work with this one. So if I was to add 5 pi over 6 plus another 2 pi, then I will get 5 pi over 6 plus 12 pi over 6, and that will give me 17 pi over 6. So that angle will be one full rotation and then another 5 pi over 6. But remember, the radius was negative, so the point will still be here. So that is what we meant in that previous slide. So we could say -3 comma, and the angle could be 17 pi over 6, and that will be another representation of the exact same point. Another way to obtain multiple representations of a point is to use negative values for r, and we already tried that, the other examples. And so if you were to make r negative, then what you need to do is add pi to represent the same point. So for example, here we made r negative 3, and from the original question that we had negative pi over 6, if we take that negative pi over 6 and we add pi, then we will have negative pi over 6 plus 6 pi over 6, and that will equal to 5 pi over 6. And so that's what we have there. So, and also because if they are opposites on a line, they form a pi radians or 180-degree angle. And so that's very useful. Make sure you keep that for your formulas. And so in general terms, you could make as many points as you want by either adding or subtracting multiples of 2 pi. And I say multiples because we have this n here. So n could be a 1, a 2, a 3, or any negative number. But since they're already using positive, negative, they're already expressing that. Perhaps n is, yeah, n is an integer. So yeah, n could be positive or negative. And then that will be keeping the radius as positive. If you notice, the radius is positive in both. So the other way will be to take to start with a positive radius and then turn it into a negative radius. And when that happens, you will be adding or subtracting odd multiples of pi. And when we say odd multiples, we mean like 1 pi, 3 pi, 5 pi, 7 pi, and of course we include the positive, negative of each of those. Now the reason they need to be odd is so that it just works that there's still 100 degrees. The angle in between the 2 points is 180 degrees or pi radians. So if you were to include the even, like in this case, even multiples of pi, that's also how we can see 2n even, and 2n plus 1 is always odd. So if we were to add even multiples, then we will be adding full circles, and so that may not be what we need when we make the radius go from positive to negative. So if you don't understand what I'm saying, you might want to look at the examples that we did here up here again, and then try to relate that with the slide that has it written down with words. So now we're going to move on from now that we know how to plot the points, we're going to move to conversions. And so to establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis. And I do actually call them the same. I don't think I should, but you know, they are located exactly at the same place. And the pole is going to be the origin. We already discussed that. So polar axis, positive x-axis, and the pole is the origin. They coincide. Not that they are the same, but they are located at the same exact place. So because any point xy lies on a circle of radius r, it follows that if we were to trace those concentric circles that we were using to graph, every point will have a radius, of course, but they will also have an angle. And if we trace a vertical line from that point to the polar axis, you could see that we have a triangle. Now, of course, if that point is on the first circle of radius 1, that will be the unit circle. But based on similar triangles, we already discussed that back in like chapter 4, that using similar triangles, that's how we can have the same trigonometric values. So if I was supposed to find the cosine of theta based on this triangle, or let's say the bigger triangle, let's use the big triangle. So that is r, which is the hypotenuse of the triangle. And then we have here x, which is gonna give us the adjacent side of the triangle. And then we have here the vertical side, which is y, and that is going to give us the opposite side of the triangle. And I say opposite because it's opposite to the angle that we have here, theta. So cosine of theta is going to be adjacent, that's x, divided by the hypotenuse, which is r. So if I want to solve for x, this will be x is equal to, the r is multiplying here. So what we're going to do is take it across the equal sign. So it will go from from dividing to multiplying. So it will be r cosine theta. Okay. Oops, I didn't leave room for theta. R cosine theta, and that's how I'm just going to rewrite it. R cosine theta is equal to x. And similarly, we could find a relationship for sine. So sine of theta is going to be opposite over hypotenuse. So the opposite is y, and the hypotenuse is r. So y will be equal to r times sine theta. And so that is how we could go from xy to polar, or vice versa. And I mean, it also depends on what we have. So from chapter 1, we learned that the equation of the circle is in standard form, it's x minus h squared over, no, I'm sorry, I'm still thinking about hyperbolas and ellipses. So it's that plus y minus k square, and that is r squared. Okay, so here with the center, we know is the center is always at h comma k. And so because we don't have an h here, we know for sure that the center is at 0, 0, which it makes sense because we are always going to consider that origin as the center of the circles. And remember, we do refer to it as the pole. So now we know how to find x, and we know how to find y. If we were to know, of course, the coordinates in polar form, because remember, coordinates in polar form will be given as r, comma, theta. And so if you know that, you could substitute r here, and you can substitute theta there to find y. And you could also substitute here and here to find x. So that's probably what we're going to do on the next example. And let's see what else. So we already have those relationships. We know how to solve for them. We have that here. That's what we did here. R times cosine theta is x. We have that here. And we do have that r times sine theta is equal to y. So we have that there. Now, how can we go? And this is to go from polar to rectangular. So this is when you start with r theta and you turn into a rectangular coordinate such as xy. Now, how can we do the reverse of that, meaning going from rectangular xy to polar r theta? So one relationship that we could always use if we know x and y is going back to that triangle. If we look at this triangle and I ask you what is the tangent of theta, and you know tangent is the opposite over adjacent. And so the opposite in this case is y, and the adjacent is x. So y over x. And that is tangent of theta, y over x. So if we know x and we know y, then it's pretty simple to find that by, of course, finding tangent inverse or arctan of that y over x. Then how could we find the radius? Because remember, we have x and y. We already found how to find theta by using that relationship here. But now, how could we find the radius? So the radius, by following the equation of the circle, will be r squared equals x squared plus y squared. So if I was to solve for r, it will be the square root of x squared plus y squared. And where are x and y coming from? Well, that's what we started with, x and y, rectangular form. So it's actually pretty simple to find that out. So for example 3, we're going to convert from polar. Here we have polar coordinates, and we're going to convert that to rectangular coordinates. So what we're aiming to do is to go from r theta to x, y, like that. So the radius does not have to be an integer. It could be an irrational number. So the fact that r is equal to the square root of 3, there's nothing wrong with that. And then we have that theta is equal to pi over 6. So let's go ahead and using the two formulas that we discussed above right here. Those are the two formulas we're going to use. We have that x is going to be equal to the square root of 3 that's the substitution for r, times the cosine of the angle, which is pi over 6. Then to find y, we're going to substitute r with the square root of 3. So it will be the square root of 3 times sine of theta. So here we're going to replace the whole cosine of pi over 6. Don't leave the word cosine anymore. And here, sorry, I made a mistake. I should replace that with pi over 6. So remember, those two go together. So the cosine of pi over 6 is equal to the square root of 3 over 2. So this is going to equal to the square root of 3 times the square root of 3. So that's the square root of 3 squared over 2. And so that will make x be equal to, here the square root and the square will cancel. So it will be 3/2. There we have it. Now let's find y. So this will be y is equal to the square root of 3 over 1. And we replace the whole expression, all of it. The sine of pi over 6, that is my favorite. Sine of 30 is 1/2. And so we multiply horizontally. So the square root of 3 times 1 is the square root of 3. 1 times 2 is just 2. So that is the y coordinate. So our point went from being square root of 3 comma square root of 6 to be 3/2 comma the square root of 3 over 2. And you could see here they're graphed, both of them. We have it here in polar form, and then we have it in rectangular form right here. Same point. So to convert a rectangular equation to polar form, we will replace x by r cosine theta. This should be together, like the r should be here. And then y by r sine theta, but you already know that. So this will be x, and this will be y. And actually, before we do start that problem, before we get into equations, I would like to do an example of how to do it the other way, how to go from rectangular to polar form. So I'm going to pause the video and find one from our textbook. So we have here example 4, and we have a point, and it is in rectangular form. So we have an x, we have a y. So x is equal to -1, and y is equal to +1. So to convert this to polar, we want something that is going to be in terms of r theta. That's what we want. So let's see, to find theta, we could use the relationship tangent inverse of y over x. So I'm going to substitute my values that I have for tangent for x and y. So it's going to be negative the tangent inverse of y, which is +1, over -1. So what I'm doing is what I'm looking the tangent inverse of is the tangent inverse of -1, right? Because we have negative and positive. So at that point, we could have two solutions because we know tangent is negative in quadrants 2 and also in quadrant 4. So the best thing to do here, and I really hope you guys listen to me, is to plot the point in rectangular form, because that will tell me which quadrant I want, and therefore I will know which angle should be the answer. So -1 for x, +1 for y. So we're talking about a point there, which is in quadrant 2. So that tells me a lot because I know the angle is going to be from here to there. And it is going to be, and actually, if you were to put in this in the calculator, pause the video and type this question on your calculator, and you will probably get a negative answer. And what the calculator will tell you is that the angle is here and it's negative, and it's going to be negative pi/4 or negative 45 degrees. But if you plot the point, this point that I have here, that has nothing to do with the point. So that's why you need to graph it. So, or plot the point in rectangular. So you know that negative pi/4 makes no sense at all. So the answer, you have to use your imagination so that you know that it's not negative pi/4. In reality, it's pi/4 before it gets to pi. If this is pi, so we are talking about 4 pi/4 minus pi/4, which is 3 pi/4. And so that's what theta will be. That is the correct way to find it. Now, to find r, we will use the square root of x squared plus y squared. So r is going to be the square root of -1 squared, that's x, plus +1 squared, that's y. And this will be the square root of 1 plus 1, which is the square root of 2. And the square root of 2, that will be r. So that's what we will use to write down our point in polar form. So it's going to be the square root of 2 comma 3 pi/4. So please, if you are converting first from rectangular to polar, first plot the point in rectangular form so that you know that you're getting the angle in the right quadrant. That is the best advice I can give you for today. So now moving from from points to equations, we're still going to use the same conversion system. So if we're replacing, if we're going from rectangular to polar equations, we will replace every x with r cosine theta, as you can see here. This little x was replaced with r cosine theta. And then we will replace every y with r sine theta. Remember those, we discussed those relationships on the previous slides. So from here, what we will do, just to simplify it, we will go ahead and expand or distribute, I should say, the exponent that we have here. So it goes to r, but it also goes to cosine. So we have r squared cosine square theta. So I'm going to take the r that we see here, I'm going to take it to the other side of the equal sign. So it's going to go from multiplying to dividing. And so we will have sine theta is equal to r squared over r. And I'm going to do something similar with cosine square theta. I'm going to take it to the other side of the equal sign. And so just like it's multiplying here to r squared, once I cross it, it will turn into the inverse operation. So it will be dividing here. So cosine squared theta. So now I'm going to keep working to the right side. So this fraction here, I'm going to split it into the following, just for convenience. So it's going to be 1 over cosine squared theta. And then the other one will have sine theta over cosine theta. And so what I'm splitting is the 2 cosine theta, not 2 cosine theta, I'm sorry. And actually this shouldn't be square anymore. So I'm going from cosine squared theta to cosine theta times cosine theta. That will be the exact same thing as cosine squared theta. So that is equal, and then if we use our rules with exponents, we subtract the exponents there. So r squared divided by r will just be r. And from here, we could use identities. So 1 over cosine, the reciprocal identity for that is equal to secant theta. And the quotient identity for sine of theta over cosine of theta is tangent theta, and that is equal to r. So when we, most of the time when we're working with rectangular equations, we want to leave them in terms of y so that, we could graph them. So in this case, we will leave them in terms of r. And sometimes they might be r equals an expression like that, but sometimes it could just be a number, r equals 4, for example. Or sometimes we could just have theta equals pi over 2, or something like that. Just like when we have rectangular equations, we also have some that could be y equals to a number, let's say 5, and that will be a horizontal line, or we could have something like x equals to 2, and that will be a vertical line. So it is also possible that we could have just theta equals something, r equals something, or we could have both r and theta into our equation. So the last thing we'll do is convert from polar equations to a rectangular equation. So now we want things that might be like x equals to something or y equals to something. And let's see, we could have perhaps some lines, maybe some circles. So let's see what we're going to find. So the very first one is only defined in terms of r. Remember, I told you that was okay. You don't have to have both variables all the time, r and theta. So if we had just r equals 2, imagine that you have your polar graphing paper. And so if I'm telling you that it doesn't matter what the angle theta is, r will always be equal to 2, then what I'm saying is that it doesn't matter what the angle is. We're only going to focus on the second circle. And that is what will shape what will be the graph of that equation. So here you have to use some imagination. And remember that the equation of a circle in rectangular form, it is r squared equals x squared plus y squared. And so if we were to just substitute the r equals 2 into the equation, like you can see here, instead of r, we're just putting a 2, but keep in mind that it's still square. So we're still following that pattern. We just substitute r with a 2. And I mean, it could be just written like that, or we could also write x squared plus y squared is equal to 4. And that has the exact same meaning as 2 squared or equal to 4. And that will be the equation in rectangular form. Rectangular equation because we do have both x and y. Now the next question was theta is equal to pi over 3. So now this is kind of like the opposite case of the r equals 2. Now it doesn't matter what r is, we're always saying theta is pi over 3, pi over 3, pi over 3. So r could be like 0, it could be 1, it could be -2, it could be any number for r. It doesn't really matter. So then in that case, what we're going to focus on is on the angle that happens to be at pi over 3, which is like 60 degrees. And so at that point, it doesn't matter what the radius is. We're always going to have those points at every single radius. And remember, they don't have to be integers. They could just be any number. So when you put that collection of points, that is what will make a line. And of course, we're saying r could be negative. So we could also go in the other direction. And that's what will form that line. So a way better representation of that you could see here. And that will be the angle right there. Pi theta is equal to pi over 3. And so we go in this way. And there we go. That is what will give you a line. Now, how could we find that line, the equation of that line? So the formula that we had before, tangent of theta is equal to y over x, is going to come in very handy here. Of course, we were using it to find theta, so it was more like theta is equal to tangent inverse of y over x, something like that, right? So if we look at the value of tangent of pi over 3, you will get the square root of 3. Now, that square root of 3 has a denominator of a 1. So what we're saying here is that y is equal to the square root of 3, and x is equal to 1. So if we have x equals 1 and y equals the square root of 3, since this is a proportion, even if I say, let's say 2 times the square root of 3 will be equal to 2, right? If you multiply it by 2. So just like I can do that, if I have the ratio here, I could say that the square root of 3 times y is equal to x. So we have that constant, the square root of 3, that needs to get multiplied by x in order for us to get y. So if our input is a 1, this probably doesn't make a lot of sense. So let's say our input is a 1 and we have a function and we don't know what the function is doing, but we have here a 1, right? And we need to find what this constant will be, which will be actually the slope. So if the input is a 1 and then the output turns out to be the square root of 3, that must be because it was multiplied by the square root of 3. And so remember that 1 was representing x. And so the equation will be the line, and you could also recognize the shape of it is a line. and that will be the square root of 3 for the slope, and then x, because it is in rectangular form, in this case, is a slanted line, so we do need both variables, x and y. And we have our last problem here, and we have the graph of the polar equation r secant theta, and it's not so obvious just by looking at him. However, we could figure this out. So if you recall, we have the relationship that x is equal to r cosine theta. So if we have r is equal to secant theta, then we're saying that r is equal to 1 over cosine theta. And if, for example, I want to solve for r here, that will be r is equal to x over cosine theta. Actually, no. I'm just going to get rid of this, look at the book, and then pause the video. Well, pause the video, look at the book. Okay, so what we're going to do here, and I'm going to just delete this so we can start from the beginning. The relationship that we had was r cosine theta is equal to x from previous slides. Now here we have a new equation that we have to convert into a rectangular equation. So what we're going to do is I'm going to solve for r here, and this is going to turn into r is equal to x over r cosine theta. I'm sorry, not r cosine theta, but only cosine theta. So right here, r cosine theta, I could also write it in this form. Or the cosine theta on the bottom will be the same as 1 over cosine theta times x, like that. Well, that 1 over cosine theta, it just happens to be the same as secant theta times x, or we could just put the x on the front so it looks a little nicer. So r is equal to x times secant theta. So I'm using the reciprocal identity of this one and replacing it with secant theta. So now what we're going to do is take this part, secant theta, and we're going to say because r is equal to the other r. So what we're going to do here is replace, not replace, but equate one to the other. So for example, the one that I obtained from here, instead of this r, is going to be x secant theta. And then on the right side, what I'm going to use is the equation they gave me, r equals secant theta. And so now what I'm going to do is solve for x. And so the easiest thing to do, you could see, is to take that secant theta, take it across, and so that will turn into x is equal to secant theta divided by the secant theta that I just moved across. And so what is that equal to? It equals to 1. And so x equals 1 is just that vertical line that we have there, and it does go across that point that it is at 1, 0. And it is vertical because it doesn't matter what the y value is, the x value will always be a 1. And that's how we get the line.